Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will start with rocket problems and we will continue with them in the next video. First of all, we will understand how to set up a recoil problem, that is a simplified version of a rocket problem. Then we will understand the steps in general to carry out the setup for a rocket problem. And then we will use our momentum principles to find the rocket equation. So let's start! Great! Let's start setting up our recoil problem. Imagine you are in a cart and you're going to jump off of it. At first, we're going to understand a reference frame at rest. Therefore, we're going to have our cart right around here and a little person that is over here. They are going to be at rest. And in here, this is going to be, well, the ground frame. Let's draw it in this timeline. At first, we're going to have this at the ti, the initial time, and then the person is going to jump off the cart. Therefore, because momentum has to be conserved, the person will go in this direction with velocity v person, and the cart will go on the opposite direction with a velocity vz. And this is at the final time. But now it's pretty useful in rocket problems and in every kind of physical problem to switch between different frames. Therefore, we're going to understand how we will do that in this simple rocket problem or recoil problem, really, so that we can do that when we are solving more complicated rocket problems. Therefore, if we have a frame that is going with the car, let's call it car frame, for example, we have a frame that is going to go in that direction at velocity vz. Therefore, initially when we're at rest, we're going to be moving backwards at velocity vz. So this is going to be going in this direction. They have the same magnitude but opposite directions. And then when the person jumps, the cart is going to be moving at velocity vz with respect to the ground. However, our car frame is also moving at velocity vz in that direction. Therefore, the velocity of the cart is going to be 0. It's going to be at rest. And the velocity of the person is going to be another one, different from that Vp. So we'll call it u. Now we need to understand what this u velocity is. Let's see. We know that u is defined as the velocity of p, the person, in the car frame. Alright. However, we also see that this u is the relative velocity of the person with respect to the cart. So these two things are the same. The velocity of p in the car frame or the relative velocity, relative v. Therefore, we can easily calculate u using this notion in terms of the final time of the ground frame. And we see that u, the relative velocity, is going to be equal to b p minus bc, this bp and this bc. And this will be a very useful tool to translate the situation between the different frames, which will be a very important notion when solving rocket problems. However, this is not the end of the story, because there is something more deep about this. Bz is really the velocity of our moving frame. Therefore, we can say that the velocity of the person in the ground frame is equal to the velocity of the person in the moving frame plus the velocity of the moving frame, which is bz, but we are going to denote by b. And this is really what gives you a more deep understanding of the situation. Great, let's understand the steps to set up a rocket problem. First of all, we need to select a reference frame. Select a reference frame. Sometimes the ground frame or the static frame will be the most useful. However, we will usually need to convert between different frames to solve our problem, and the notions we gained before will be very useful. The next step that we need to do is to consider the state at time t. At time t, that was our old t initial that we had, and at time t plus delta t. Really, in Recoil problems, we have a mass transfer that occurs in 1 second. In rocket problems, we are going to have continuous mass transfer, and therefore it's going to be like solving a recoil problem but for every single second. And when doing something like that, calculus will help us a lot. Once we have done this, that is exactly the same thing we did on our recoil problem, we can draw momentum diagrams. Draw momentum diagrams. Momentum diagrams. This is the step that we didn't finish doing, we started, but we will have to denote also the masses of the objects to do it. And by using momentum conservation, the recoil problem we did earlier was easily solvable to get in the velocities and all the final result of the system. In doing this, we will use our momentum principles after that to get what happens with the system. Note that at time t plus delta t, rockets are going to be exposing lots of fuel to propulse themselves. So in our momentum diagrams, we are also going to consider that fuel that was propulsed down. These are the fundamental steps to solve and set up rocket problems. Alright, now we're ready to set up our rocket problem and find our rocket equation. First of all, we need to select our reference frame, and we are going to do most of our work on the ground frame. However, we're going to use some notions of the rocket frame later on, and you will see how our recoil problems will be useful. After that, we will need to understand the two different times and states at time t and at time t plus delta t. And let's see why that's important. Recall that F external, as we saw in our momentum video, right around here, equals the time derivative of the momentum. And by definition, this is no other thing than the limit as delta t goes to 0 of p at t plus delta t minus p at t divided by delta t. Therefore, as we see, we need to consider our state at time t plus delta t and our state at time t. Let's start drawing our state and then our momentum diagrams. We're going to have our rocket. This is going to be at time t, right around here, time t, and we're going to have a velocity v of r, and our rocket is going to have a momentum a mass, mr of t, and the velocity is also going to be time dependent. Then at time t plus delta t, we're going to have our rocket over here. We're going to have a different velocity v of r of t plus delta t. We're going to have a different mass t plus delta t, and most importantly, we're going to have a little bit of fuel that has been expelled, and it's going to be a delta mf that is going to have a velocity down that's going to be v fuel. However, from the rocket perspective, it's really hard to know which velocity is this, because it depends on the velocity of the rocket and also the relative velocity. So it's a very more useful notion for the rocket problem to talk about the relative velocity of the fuel. Therefore, this fuel is going to have velocity u in the rocket frame, the relative velocity, and we know that this velocity in the rocket frame plus the velocity of the rocket frame, which is precisely the velocity of the rocket at time t plus delta t in this case, it's going to be equal to the velocity of the fuel at time t plus delta t. Now we also need to consider something about our little mass, and that is that we're going to consider mr of t plus delta t as mr of t plus a little small mass element that has changed. And note that this change in mass has to be the same change but opposite to this change, because mass in our system has to be constant. Therefore, and we are starting with conclusions, this delta mr has to be equal to minus delta mf. Alright, now let's see what our momentums are in these different situations. Our momentum at time t is simply p of t is simply equal to br of t times mr of t. That was a weird order to put it, but it's alright. And our momentum at p of t plus delta t, p of t plus delta t, it's going to be equal to this component. Let's see, it is br of t plus delta t and mr of t plus delta t, but we said that that was mr of t plus delta mr. So this is mr of t plus delta mass of the rocket. And we're going to have a component arising from the fuel. Therefore, we're going to have a plus delta mf times the velocity of the fuel. And this is going to be the momentum at time t plus delta t. Now let's input all of our information on the external force. Let's see, we have that our external force is going to be equal to the limit as delta t goes to 0, as we saw earlier, and we're going to have p of t plus delta t. Therefore, this is going to be mr of t plus delta mr. Let us drop the time dependence of the mr. Let's assume it's implicit. Plus delta mr times the velocity, very importantly, at t plus delta t of the rocket, t plus delta t. And this delta mf, we're going to substitute directly our delta mr. Therefore, this is going to be minus delta mr. And we are also going to substitute our expression for bf of t plus delta t, which is this right on here. That is u plus br of t plus delta t. And now we just have to input the momentum of our system at time t. That is mr times b of t. And all of this is divided by our time element. Now let's start grouping terms and try to form derivatives out of this. Let's see, we're going to have once again our limit as delta t goes to 0. And let's group the mr terms. We have an mr and we have br of t plus delta t. So br of t plus delta t minus, we have it over here, mr minus b of t over delta t. And we recognize this is a time derivative of velocity of the rocket. And now let's group the delta mr's. So we're going to have plus delta mr, and we're going to have br of t plus delta t minus u minus br of t plus delta t. All of these over delta t. And this is a little bit harder to see these consoles, and in general a velocity divided by a time element isn't anything, but note delta mr, it's no other thing than mr of t plus delta t minus, if we take that to the other side, mr of t. So what we really have here, it's a time derivative of the mass of the rocket. Now, if we write all of these derivatives, we are going to get, I'll write that on blue, that the external force that the rocket feels is equal to the time derivative of the velocity times the mass of the rocket, so that's dbr dt vector and vector, plus, well, minus, because of this minus in here, the time derivative of the mass of the rocket times the velocity of the fuel with respect to the rocket. And this is the famous rocket equation. Next time, we will try to understand it more completely. That is all for today. I hope you liked it and that all these recoil problems and the steps to set up the problem, and then using our momentum principle and all the concepts to get to the rocket equation, help you understand everything. Any doubts left, you may ask them in the comment section, and remember that next video we will be clarifying all of this and understanding the rocket equation completely. Remember to like the video if it was the case, subscribe to the channel, press the bell and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!